A very good evening to all dear lovely students. I hope you are doing well. Welcome back to the YouTube channel Shri Chaitanya Gosala. Myself Anirudh Mehta, and today in this chemistry class we'll be continuing the next topic of physical chemistry. In the previous class I have told you about unitary method, where I showed you how to solve questions of mole concept and also the questions from electrochemistry as well as that of chemical equilibrium using just the unitary method. Today in this lecture I have taken another very important topic, which is nature of electromagnetic radiations, from the topic atomic structure. Nature of electromagnetic radiations. The same chapter is going on in the classes as well, so I thought before you come back and join here, we should discuss the same thing here as well on the YouTube. So, if we talk about the model of atoms, how the development occurred, how the development occurred was, first Dalton gave you the model in 1803, which was Dalton's model of atom, which he said atom is indestructible and we cannot have anything smaller than atom. We obviously failed him. So in 1803, Dalton was the first person to talk about what an atom is. He said atom is indestructible, right? Too much time passed. Around 1879, first time Faraday could generate electricity out of the gas, and he discovered the cathode rays. Cathode rays, right? And similar time anode rays were found in 1886 and so on. Around 1897 is the first time when people came to know that yes, atom can be further broken down into smaller particles like electron. So electron was discovered by J.J. Thomson. So you can see how much time it took from 1803 to 1897. Almost 95 more years it took to just prove Dalton's wrong. And then after J. Thomson discovered the electrons, around in 1912 proton got discovered. At this time around, Rutherford gave his model of atom. So here around in 1898, around in 1900s, J.J. Thomson gave his model, which was plum pudding model, and then Rutherford gave his model around 1912. Okay. At this point of time, now it comes to failing the Rutherford. Hello, beta. Katuri Balakrishna, what's your name? Okay. So, Rutherford model came around this time only, and Rutherford model had to be discarded because of the topic nature of electromagnetic radiation. We said Rutherford is saying that electron revolves around the nucleus, but this time we were always believing in a theory of Maxwell, James Clerk Maxwell. We'll come to that in 5 minutes. I'm just telling you the history right now. So James Clerk Maxwell had said whenever charged particle is accelerated, like an electron is revolving around the nucleus, it's an accelerated motion. It should generate some energy continuously. It should emit some energy continuously. And then finally that electron should get tired and fall down into the nucleus, and the atom must collapse. But it never happens. Atoms are stable only. So here at this point of time we wanted to prove how Rutherford is wrong. So we have to study about nature of light. Nature of light. Okay. So at this point of time we wanted to talk about what the nature of light is. Actually 3 people have contributed in this. First person is Newton. He thought that light is of particle nature. Light is of particle nature. Okay. Nobody believed him. Newton, this was long time back, he believed that light has a particle like nature. Then James Clerk Maxwell said that I can prove that light has a wave-like property. He could prove it with diffraction and interference pattern. These patterns are shown only by the waves. He found that a light generated from any source, like the light coming from the bulb, when passed through a double slit shows interference pattern, that means it has to be a wave. So James Clerk Maxwell says it acts like a continuous wave. We'll talk about this theory today. Wave-like nature. Wave-like nature. On the other hand, after a few years of James Clerk Maxwell, after he said that it's a wave-like nature, he was unable to explain a few experiments like photoelectric effect. Why does it happen? Because wave-like nature cannot explain the photoelectric effect. It cannot explain about how the black body changes color when we keep heating it. So then came our Max Planck, who gave a theory which says that Maxwell, you are correct only, it has a wave-like nature, but Newton was also correct. That means it has a dual nature. It has particle-like and also wave-like nature. So light has a dual nature. And this is the most latest theory about light that we know, that light has a dual nature. In a nutshell, if I want to tell, if this is the source who is providing you light, let's say it's a bulb, Newton thought that light travels in the form of packets like this. He has no idea about the wave. So this is what Newton is thinking. Okay. We don't generally study the theory of Newton because it's a very old theory. It's a very discarded theory right now. Maxwell thought that light is released continuously in the form of a continuous wave of a constant wavelength like this. This is what Maxwell thought. He could explain the wave-like nature by doing the experiments like diffraction and interference, but was not able to explain how photoelectric effect happens. Then Max Planck says, you are half correct, you are also half correct. Actually, light comes in the form of wave in discrete quantas or packets like this. So this is the real way how the light should travel. It actually travels like a wave but hits like a particle is what Planck said. So you should remember, this is the newest way of telling what Max Planck had said. Planck's quantum theory. So these are three things, two theories we are going to study today. Let's talk about Maxwell's electromagnetic wave theory. So he gave the theory as Maxwell electromagnetic wave theory. Electromagnetic wave theory. After failing it, we'll go to Planck's quantum theory. Planck's quantum theory. This is our aim today. So these two topics I have taken for you. Yes, we have started the new topic only, beta. We have started the new topic only. This is not the topic of last class. It's a new topic only. So Maxwell's and Planck's theory, these two things we are going to talk about today. Right. So let's quickly brush up our concept with the Maxwell's electromagnetic wave theory. We'll ask him one by one, what are you talking about these waves and how do we produce them? So he tells you point by point. First thing, for few postulates are there, we must remember those postulates. He says, whenever any substance is heated or any electrons or any charged particle is accelerated, then some energy gets released. I am calling them electromagnetic radiations. Okay. So number one, accelerated charged particles or any heated source or accelerated charged particles produce oscillating electric and magnetic fields. We'll talk about it. Whenever any source is heated, let's say I heat a tungsten filament. From here, it will release energy continuously on the form of waves is what Maxwell is telling. Or whenever any charged particle of a plus minus q charge is accelerated, then also it releases some energy continuously. He is calling this energy as radiant energy. Radiant energy. He calls it as electromagnetic waves, or he calls it as radiations. Okay, all of them mean the same thing. So first thing he says, how do you generate these radiations is either you heat something, okay, or you can accelerate a charged particle like an electron. Number one point is clear. Then we ask him, what are they made up of? He says they are made up of two components. That's why the name is electromagnetic waves. So they are made up of two components. They have a oscillating electric component and magnetic component. So we ask him, how do these components look like? He says the electric component and magnetic component both are oscillating perpendicular to each other. Both are oscillating perpendicular to each other, and both are mutually perpendicular to the direction of propagation of wave. Very important. Let's say, with the help of a diagram, I will show you. If let's say this is the bulb, it is propagating the wave in the x-axis. So this is the direction in which wave is moving. The radiation is moving in x-axis. This is the direction of propagation of wave. He says the electric field will be perpendicular to the direction of propagation. So electric field, let's keep it on the y-axis then. This y-axis, I am keeping electric field. So in the y-axis, electric field will be oscillating in the form of a wave like this. So it has first component, which is the electric component, electric field component, which is in the which axis? Y-axis. And then he says it has one more component, which is the magnetic component, which will be in the perpendicular to both of them. So which will be magnetic component will be perpendicular to both the electric field and the propagation of the direction of propagation. So let's say in the x-axis our wave is moving. Okay, perpendicular to it in the y-axis, I am saying electric field is moving like this, oscillating like this. Magnetic field will be perpendicular to both of them, means perpendicular to x also, perpendicular to y also, which will be the z-axis. So in the z-axis, your magnetic field will be oscillating like this, which will be coming out of the notebook and going in the notebook, coming out of the notebook, going in the notebook, coming out of the notebook, going in the notebook, like this, like this, like this. Okay, if I show it in 3D, I'll just shade it out so that it looks more clear to you. So whichever wave is coming out of the board, I am just shading it so that it looks little 3D to you and you are able to understand it. Okay, something like this. So he says, first thing I told you how to generate these waves. Second, he's telling what are these waves made up of. So they are made up of two components, electric and magnetic. And these electric and magnetic components are perpendicular to each other and mutually perpendicular to the direction of propagation of light or wave. Okay, something like this. I hope it looks clear to you. Next point, we ask him, the waves that you're talking about, electromagnetic waves that you talk about, do they require any medium for traveling? Are they like sound waves? Because sound waves can't travel in vacuum. He says, no. These light or these electromagnetic radiations can travel without any medium. So they do not require any medium for propagation. I have written it here at this point. You can just read it out. Electromagnetic waves do not require any medium for propagation. They can travel in vacuum as well. They can travel in vacuum as well. Now my question to you, my dear students, is, next point we ask him, what do you think is the speed at which they travel? Who travels faster? Who travels slower? We have different types of electromagnetic radiation, all of you know, X-rays, gamma rays, UV rays, visible rays. Who do you think travels faster? If I ask you between X-ray and visible ray, for example, or X-ray and radio waves, among X-ray which has very low wavelength, X-ray looks like this, versus radio waves which have very high wavelength. Radio wave looks something like this. Who do you think travels faster per second? Quickly tell me. Who do you think travel faster per second? Is it the X-ray who will travel fast, or is it the radio waves who will travel faster? What do you think? Quickly tell me in the chat box. I am seeing your comments. Class timing daily will be notified to you, beta. Who would travel faster? What do you think? He says electromagnetic radiations of all types, whether it is X-ray, gamma ray, cosmic ray, radio waves, microwaves, IR, they all travel with same speed, which is nothing but the speed of light. All of them are lights only. They are not carrying any real particle which has a mass, that one is heavy so it will travel slowly, one is lighter so it will travel faster, nothing like that. All of them travel with the same speed, that is speed of light. So remember this point, they all travel, all types of electromagnetic waves travel with same speed, that is C 3 into 10 power 8 meter per second in vacuum. Obviously you know that speed of light changes in other mediums, but in vacuum all of them travel with the speed of light, 3 into 10 power 8, same speed they will have. So if a question is asked to you, two electromagnetic radiations have a wavelength ratio 1:5, what is the ratio of speed? You say 1:1. Speed will be same in ratio, 3 into 10 power 8 meter per second. So this is the one, right? So this is how these waves look like. They are perpendicular to each other and to the direction of propagation of wave. These are the points told by Maxwell. Now he says, whenever you want to know about a wave more, you should know its characteristics. The characteristics of waves are, few of them, like if you want to know about a person, what do you ask? You ask for its name, okay? You ask for the place. Same way, when you want to know about a wave, you ask for its wavelength, which will represent as lambda, which is nothing but length of one complete wave. A wave starts from the starting of a, we'll call it crust, the one which goes up is crust, the one which comes down is the, negative amplitude, that is called as trough. So starting from a crust to the ending of a trough, we call it as wavelength. So if this is a wave, if I'm showing here, if I show you the wave here, okay, let me show you a wave here in this area. Generally, when we show a wave, we show only one of the component. You don't have to show both electric and magnetic component. Just one component is sufficient. Just one component is sufficient. Something like this. Now, from the starting of a crust to ending of a trough, this is one complete length of wave. We call it wavelength. We call it wavelength lambda. This is the most important characteristic of a wave. Length of one wave. You can take it from starting of a crust to ending of a trough like this, or you can take it between two peaks. Both are same only. This is also lambda. Distance between two consecutive crusts or two consecutive troughs. Okay, this is the one. Next is frequency. So I'll just show you what are these things. Wavelength, I just told you what is wavelength. It is distance between two consecutive crust or trough. Units will be, SI units will be meter. Generally, because wavelengths will be so small, we'll be using it not in terms of meter, we'll be using in terms of nanometer or angstrom. A nanometer means 10 power minus 9 meters. A angstrom means 10 power minus 10 meter. So mostly because wavelengths will be very small for light, we'll be using always either nanometer or angstrom as the units. Right, beta? Next is frequency. Frequency. Frequency means number of waves which can pass through a point in 1 second. Number of waves which can pass through a point in 1 second. So its units will be number by time. Number by time. Number doesn't have any unit as we know. So it is just time inverse. So units of frequency will be time inverse or hertz. A hertz means a second minus 1. Okay. Hertz mean second minus 1. So this is frequency. So units are second minus 1. Now generally frequency of the light will be so high, which will not be studying in the terms of hertz, but will be studying in the bigger units like kilohertz, kHz. You might have seen that whenever you are, surfing through the radio, you see the frequency in kilohertz, or whenever you purchase a new computer, you will see the frequency in kilohertz. You will say the processor is 2.5 kilohertz, like that. So kilohertz is the frequency, means you have to convert it to hertz, means it will be 10 power 3 hertz. It may be given in megahertz, MHz. You can say it is 10 power 6 hertz. It may be given into you in gigahertz. Giga means bigger than mega, 10 power 9 hertz. Okay. Now by unitary method, you can easily derive what will be the value of this frequency nu. What will be the value of this frequency nu? Okay, we'll see that. Next is wave number. Wave number will be represented by nu bar. This is represented by nu, it is not V, it is nu, symbol is like this. Next is wave number. That means how many waves are present per unit length. So if I draw a 1 meter line, in that 1 meter line, how many waves will be there? Its formula is 1 by lambda. Again, by unitary method, you can solve this as well. So wave number will have a units of meter minus 1. Will have a units of meter minus 1 or centimeter minus 1 or so on. Okay. Now let's talk about what are the formulas that we require here. Formulas required for Maxwell's theory. Formula required. First formula is, let's do frequency versus wavelength. Frequency versus the wavelength. Okay. Frequency versus the wavelength. Frequency is equal to C by lambda. Frequency is equal to C by lambda. Call it as equation 1. Let's learn these equations first and then we'll see what are the numericals possible from here. Second, how do we relate wave number versus lambda? Most of you would be remembering these formulas. You can obviously derive them with just unitary method, but let's quickly learn them and move ahead. Wave number is the reciprocal of wavelength. So second one is wave number is the reciprocal of lambda. Call it as equation 2. Okay, call it as equation 2. Now if I relate these two things, I can put 1 by lambda as wave number here. So I can also relate frequency versus wave number. So frequency, which is C by lambda, I can take 1 by lambda as nu bar, I can say C nu bar. Call it as equation 3. These are the three equations which are required from Maxwell's theory to continue further. I think if you remember, this one is also sufficient. Frequency equal to C by lambda. Frequency equal to C by lambda. Right. Frequency equal to C by lambda. Now, moving ahead, let's see what are the type of questions you can get from here. According to Maxwell, electromagnetic waves are produced by how are they produced? Charged particle at rest? No, when the charged particle is in acceleration. Uncharged particle in motion, they can't produce. So when planets move around the sun, planets are not charged particles, so they don't release any energy. That's why planetary motion doesn't need any explanation. No energy gets released when planets revolve around the sun because they are not charged. Accelerated charged particle, this is correct. So when electrons are revolving, they should release the energy continuously as per Maxwell. Okay. Neutrons moving with constant speed is also not correct. Neutrons are not charged particle, and at constant speed anyways, energy will not be produced. Which component of electromagnetic wave is responsible for visual sensation? Okay. Which component of electromagnetic wave is responsible? Both are responsible. Both are responsible. So these are some of the questions which are written here. In vacuum, all the electromagnetic waves travel with in vacuum, all the electromagnetic waves travel with. I told you they travel with the same speed, so frequency will not be same. Frequency will be more for a X-ray or a gamma ray as compared to visible. Same wavelength is also not true. Wavelength will be characteristic of a wave. Each wave of different type will have different wavelength, different frequency. Same velocity is correct, that is correct. Different velocity is wrong. Okay. Now, why did we fail the electromagnetic wave theory? First, we'll write down that electromagnetic wave theory could explain about phenomena like interference and diffraction. Interference and diffraction. Okay, interference is, we will study it in the physics in the topic maybe wave mechanics, where you will see that whenever a stream of light is passed through a double slit, you will see the interference pattern. You will see the interference pattern, which is dark and light bands. You will see that is interference. Diffraction would mean bending of light when it hits any obstacle. When it hits any obstacle. So whenever light hits an obstacle, it starts bending. This also will be studied along with interference in your physics only, that whenever a light is going through a slit, a single slit if I take, if a light goes through a single slit, if it is going in this direction, it slowly starts bending and it starts going in the other directions as well. So once the light splits, it starts going into different directions like this. This is called as diffraction. Once you go into physics, you will study more about it, diffraction patterns and the interference pattern. But these two things are completely physics, that electromagnetic wave theory could tell light is in the form of wave by explaining these two phenomena, but it could not explain. It could not explain about phenomena like black body radiation, photoelectric effect, and why the hydrogen spectrum is discontinuous in nature. Discontinuous nature of hydrogen spectrum. These are some of the drawbacks. Once in a nutshell, let us see, and then we will see this in the detail. Black body radiation. See beta, whenever you take a black body means any opaque object. A perfect black body is not what we are talking about. Let's take any black body like a black color spoon. You can take spoon of an iron. If you take, if you start heating it, Maxwell said that energy will be released continuously in the form of wave. A continuous wave means beta a wave with a fixed wavelength. So as per Maxwell, if on heating a spoon, if it turns red, it should remain red at every temperature, because wave is released continuously like this. No matter how much you heat it, if the red color wave started coming out continuously, that red color wave only has to come out. There has not to be any break. But we found that at a temperature of something like, at a lower temperature, the red color is coming out. Let's say at 800 Kelvin. But when the temperature got raised to something like 1000 Kelvin, slowly the color changes to green or orange, let's say, at 1000 Kelvin. And when we go ahead at 1500 Kelvin, it changes to green color. And when we go to a very high temperature, it finally changes to blue color as well at 2000 Kelvin. Now, if the color keeps changing, That means wave was not coming out continuously. Initially, the wave of a longer wavelength was coming out, the red wave. After some time, when the temperature got increased, the wavelength got decreased to orange and a lesser wavelength started coming out. Means it's a new wave. Wave doesn't travel continuously in one. As soon as the wavelength changes, it's a different wave. This wave and this wave are not same. It's not a continuous wave. These are a set of two separate waves. This is a red color wave. This is an orange color wave. Both are completely different. So Maxwell, we are asking that how the color is changing. You told us that the wave will be released continuously. Continuously means same wavelength must remain at every temperature. How is the color changing? When you go to 1500 Kelvin, it is becoming even a smaller wave of a green color, for example. And at very high temperature, it becomes a blue color wavelength, which is very, very small wavelength. This cannot be explained by the continuous release of energy as Maxwell is telling us. Okay. So we say, Maxwell, you are wrong. If he did not say that energy is released continuously in the form of wave, then this theory is right only. But he used the word continuous. So release of energy from black body cannot be continuous. It has to be discontinuous. Somewhere the wave has to break. The wave has to stop. Red color has to stop. Then only orange color can start. When orange stops, then only the green can start, and so on. So this will be explained by Planck's quantum theory, that energy doesn't travel continuously like this, but it travels in the form of packets, where each wave travels in the form of packets. At low temperature, red color packets were coming out. At high temperature, these packets mostly became the lower wavelength packets. This is what Planck's will explain. Okay. Next is photoelectric effect. We will study photoelectric effect, that whenever a surface of metal, this is a photosensitive metal, when we irradiate with the light, how does a electron get ejected from here and starts moving with some kinetic energy? This also cannot be explained by continuous nature of the light. If light had a continuous nature, this electron should come out with any given wavelength. With any given wavelength. So if energy was continuous, let's say this electron requires some 5 joule energy to come out. Okay, it's called as work function. I can take 5 of such waves, each wave of 1 joule, let's say, or 7 of such wave, 1 joule, 1 more joule, 1 more joule, 1 more joule, 1 more joule. It will become a 6 joule, and then electron could come out. But when we try to do it with low energy wavelengths, electron was never coming out. That means wavelength doesn't come continuous like this, but each wavelength hits the electron one at a time. Then second wavelength will hit, then third wavelength will hit. In a nutshell, I am telling, we'll be studying about what is photoelectric effect after some time. But it can only be explained by particle nature of the light or dual nature of the light, but cannot be explained by a continuous wave nature. We cannot explain photoelectric effect. Okay, it will be explained by Max Planck. And the nature of hydrogen spectrum also can be explained once we know about discontinuous nature of the energy. Okay, so let's do one problem before moving ahead. Problem can be asked like this. If frequency of a electromagnetic wave is 60 megahertz, find its wavelength in nanometer. Okay, I want you to reply. Kindly do this question. I'll wait for 2 minutes. I'll wait for your answer, and once you have given me the answer, I will be explaining it further. Okay, so let us solve this. So frequency is given 60 megahertz. So new value is given 60 megahertz. Mega means 10 power 6 hertz. And speed of the light we always know is 3 into 10 power 8 meter per second. And they're asking the wavelength lambda we have to find. We know nu equal to c by lambda. So frequency which is 60 megahertz, 60 into 10 power 6. Hertz means second minus 1 equal to speed of light 3 into 10 power 8 meter second minus 1 by lambda. Second minus 1 cancels out. So lambda comes out to be 3 into 10 power 8 by 60 into 10 power 6. Okay, this will become 10 power 7 and with 10 power 8 it will go 10 times. So it is coming out to be 5 meter. So lambda comes out to be 30 by 6 which is 5 meter. So in meter it is coming out to be 5. So very large lambda this is, almost a radio wave. And in nanometer I have to find lambda in nanometer. Each meter is much bigger than nanometer. 1 nanometer has 10 power minus 9 meter. So 1 meter will have 10 power plus 9 nanometer. So this is the answer. Hi Vijay Shri. Okay, right. Another one let's do. Question can be asked like this. If frequency of a electromagnetic wave, if the frequency of an electromagnetic wave is 200 kilohertz, find number of waves in 1 kilometer. Calculate number of waves in 1 kilometer. Okay, so I'll tell you what to do here. Okay, whenever they ask you number of waves enclosed in 1 kilometer, means if I take a 1 kilometer distance, if this is 1 kilometer distance, how many waves would fit inside this? How many waves would fit in this, inside this? This is called as wave number. How many waves per kilometer? So they are asking wave number. Now you think yourself, if each wavelength is some lambda kilometer, for example, we'll find the lambda in kilometer. If each wavelength is lambda kilometer, so in 1 kilometer how many waves will come? We'll say in lambda kilometer 1 wave is coming. In lambda kilometer 1 wave is coming. So in 1 kilometer, how many waves will come? 1 by lambda waves will come. So this is called as wave number. That is how we can derive what is wave number. So wave number is 1 by lambda. If you want in 1 kilometer, means you want to first find the lambda in kilometer and then do 1 by lambda. So let us see. So our first aim is to find the lambda. Frequency is 200 kilohertz. So we can say frequency equal to c by lambda. Okay. So I'm trying to find the lambda in kilometer units first. So frequency is 200 into 10 power 3 hertz. Kilo means 10 power 3 second minus 1 equal to speed of light 3 into 10 power 8 meter second minus 1 by lambda will come in meter first. So first thing, the lambda comes in meter as second minus 1. So lambda comes out to be lambda comes out to be 3 into 10 power 8 by 200 into 10 power 3 meter. Okay, lambda comes out to be 3 into 10 power 8 by 200 into 10 power 3 meter. Okay, this is in meter. I am not solving it further. I am just writing it in kilometer directly, and then we'll do 1 by lambda. So lambda comes out to be this much. So I can say lambda in kilometer comes out to be, if lambda in meter is this, meter to kilometer 10 power minus 3. So it will be 3 into 10 power 8. I can write it as 2 into 10 power 2 and 10 power 3, 2 into 10 power 5. This is in meter multiplied by 10 power minus 3 kilometer. This is the wavelength in kilometer. If I check how much it is coming out as, this is going 10 power 3 times, 10 power 3, 10 power minus 3 cancel out. It is coming out to be 1.5 kilometer. 1.5 kilometer. So wavelength is more than a kilometer. Wavelength is more than a kilometer, meaning that 1.5 kilometer mein to one wave will fit. So 1 kilometer mein less than one wave will fit. So wave number will be 1 by lambda, which is 1 by 1.5, which is 2 by 3 waves per kilometer. Answer is 2 by 3. Means only 2 by 3 wave will come in 1 kilometer, not even one complete waves. Okay, only 2 by 3 waves will be there per kilometer. These are the type of questions that we can get from Maxwell's theory. Okay. So the failure of the wave theory, I told you, it could not explain about black body radiations and about the photoelectric effect. This led to the birth of quantum physics, or we can say quantum Planck's quantum theory. Planck's quantum theory. This gave rise to the Planck's quantum theory. Okay. This is how the graph of black body radiation looks like. You can ignore this part yet, okay, because it is not very much visible right now. The colors got changed. I'll tell you how the graph looks like. You can ignore this part for now. Black body radiation. What is an ideal black body? An ideal body that emits and absorbs all radiations of all frequencies is called as a black body. Whenever we shine light on a body and it absorbs everything, it will look completely black to you. So a black body is a perfect absorber of all lambdas and perfect emitter of all lambdas. Okay, this is what a black body is. Now let us see what he observed in the black body experiment. So we'll mention, as I told you, when you take any black body, I'm taking an opaque object here, which is black in color, it's a black body, and I start supplying heat on it. It is found that at low temperature, it was emitting red color. So red color was emitted at low temperature, something like 800 Kelvin. Further heating, it changed the color. Slowly it goes from red to orange. Goes from red to orange. Finally goes from orange to yellow. Goes to green and finally to blue. So when the temperature raised to something like 1500 Kelvin, goes to green and finally goes to blue at 2000 Kelvin. That is what really happens when you heat a spoon as well. Take the spoon to a very strong heated flame. You will see that it will change color from red to blue completely. Now what is happening? We observe that as the temperature is increasing, the wavelength is decreasing because red is having high wavelength and blue is having low wavelength. So when temperature is high, low lambda photons were coming, but when the temperature was low, high lambda photons were coming out from the black body, which cannot be explained by the continuous nature as Maxwell used to think. Because I told you, as soon as lambda changes, that means the wave has changed. If initially a red color wave was coming out and after some time it started becoming something like a green wave, these are not same wave, these are two separate set of waves. This is first set of wave, this is second set of wave. Wave 1, wave 2. Okay. What would we predict now if I draw a graph between intensity of radiation versus wavelength of radiation? I'm drawing a graph between intensity versus wavelength. Intensity means number of photons coming out per unit area per unit time, and wavelength. Now first let us listen to color. Sudhir, is it working? From here I don't see working. एक बार refresh करो. Right. So the graph comes out to be something like this. It comes like a bell-shaped curve at a low temperature of let's say 800 Kelvin. This graph represents intensity, means number of photons coming out or number of waves coming out. Actually, at any temperature when you are heating the black body, all the type of photons are coming out. Some of them are red color photons, some of them are blue color photons. Because red color photons are more in number, that's why our eyes are able to perceive the color red. So maximum percentage of photons are coming out in the red color wavelength. So this is lambda red, for example. Okay. As per Maxwell, what would have happened is, if I increase the temperature, red color still should come out, maybe with more intensity, more red color it should come out. This is what Maxwell is predicting. Color should not change. Most of the photons still should be red in color due to continuous nature. Most of the photons should be still red in color, but maybe little more intensity. But this did not happen. On heating, no doubt number of photons got increased, but also the color of photon also got changed to blue color. So lambda shifted to backside and it became lambda of the blue color at a temperature of something like 2000 Kelvin. This is how a black body graph looks like. When you increase the temperature, the graph shifts up and back. Graph is shifting up, meaning intensity is increasing. So we'll mention as temperature is increased, two things happen. Number one, intensity of radiations increases. Intensity of radiation increases, meaning more and more photons start coming out. Number two, wavelength of photons decrease. So as temperature increases, when more heated photons are coming out, the heated photons are of lower lambda, means temperature is inversely proportional to lambda, or I can say energy is inversely proportional to lambda. at low energy, when the photons coming out, when the radiations coming out were a little colder at 800 Kelvin, they were of red color. 800 Kelvin pe red color was visible. So I'll just show this color as red. This is the red color. This is the temperature at which color is red. And when we increase the temperature, the color slowly shifted to blue, something like this. Energy is inversely proportional to lambda. When we remove the proportionality, we get energy equal to hc by lambda. So I can say energy is inversely proportional to lambda, or we can say energy is directly proportional to frequency, because frequency was inversely proportional to lambda. So nu can be written as c by lambda. When we remove the proportionality, we get energy equal to proportionality constant, Planck's constant, h into nu. This is our equation 2 for the day. This is our equation 2 for the day. Okay, so from here we can derive our Planck's quantum theory, and the rest of the thing let's discuss in the next classes. Okay, so I'll keep it up to here. Thank you very much. I hope you have enjoyed. Bye bye.